Today I wanted to talk about link functions and how they're used to model some atypical cases of some data. So just a quick regression overview. The ultimate goal of regression is to estimate some conditional expectation of a random variable given some data. So we have some random variable y that we are interested in, and we have some data x, and this could either be univariate or multivariate, doesn't matter. And the goal of regression is to find some function or build some function that takes in data with some parameters that basically approximates this expected value, this conditional expected value. And in some cases, like ordinary least squares, this conditional expectation is essentially unbounded, and it takes on values from negative infinity to positive infinity. So for example, pretty much most real valued data will not be constrained into some specific range of values. It can kind of just be any arbitrary real number. But what happens when this is not the case? And I think the most obvious example is a Bernoulli random variable. Since Bernoulli random variables take on values, discrete values, 0 and 1, that limits the possible values for this conditional expectation, obviously, because if I have all zeros, then the average is going to be 0. If I have all ones, the average is going to be all ones. Those are the two extreme cases, and then any other case, it will be in that interval 0 to 1. So for a Bernoulli random variable, the conditional expectation given some data is going to be in this closed interval. And so for this case, we need some slightly special treatment of our estimator f to conform to this range as the basic linear estimator, which is just basically taking the linear combination of our data with some parameters. That raw linear combination is some arbitrary real number, so it can range from negative infinity to positive infinity. And so the solution to this problem is the link function. And the whole purpose of the link function is to essentially transform this raw linear combination, this linear estimator, into the same codomain of the conditional expectation for our dependent variable of interest. So in other words, our conditional expectation of our dependent variable given some data is essentially some function g, which is called the link function, which takes in that raw linear combination and then transforms it in a way where it can use to approximate or estimate that conditional expectation. So kind of one other way to look at it is you can think of the conditional expectation itself as a function where we take in some data x and it's mapped to some set of values. This is the codomain I'm calling omega. And our link function g takes in that same data and it maps it into the same space essentially. And so just as an example, since we were talking about it earlier, for a Bernoulli, omega in this case would be 0, 1. So the conditional expectation ranges from 0 to 1 for Bernoulli random variable. And our link function, which would take in the same data, also has to map to 0 and 1. And then just as a side note, there are something called canonical and non-canonical link functions, where canonical link functions are usually the, quote, more natural link functions, and those are usually derived from something called the exponential family. But I think that topic is a little bit too out of scope for this video since it can get a little complicated, and this is mainly to serve as like a very basic general overview. So to give one somewhat practical example, we're going to derive logistic regression using a very basic, somewhat crude link function. So typically, when you hear about logistic regression, you'll most often see the logistic function or the sigmoid function being used. But here I am purposely using something stupid just to like get the idea across about how link functions work. So, as mentioned, we'll use a very elementary link function to build an estimator for Bernoulli random variables. So I have some Bernoulli data, and I'm interested in basically building a regression model on this Bernoulli data, or in other words, I want the conditional expectation of this Bernoulli random variable given some data I have. And this link function will be defined in a very simple way, where if the linear combination is greater than 1, we bind it to 1. If that linear combination is less than 0, we bind it to 0, and then otherwise it's just the linear combination. So this is essentially just like a modified identity function, where if the linear combination is between 0 and 1, then we'll just use that. Otherwise, we just truncate it at 0 and 1. And then also, we will constrain, during optimization, we will constrain beta to be, I put strictly positive here, but really it could be greater than or equal to 0. I just put greater than 0 because it's a bit easier to define in SciPy that I'm using to optimize, but it doesn't really matter. And just kind of think for a moment, like why impose this constraint in the first place? Well, I have this very beautiful hand drawing I did in Paint where we have 0 and 1 here. These red dots are basically the data points, so some samples, 0 data points and 1 data points. And then notice that this vertical line here is essentially our linear combination, so it's x times beta. And then if that exceeds 1, then we will truncate it at 1, and then if it's less than 0, we truncate it at 0. And then you'll notice that this looks pretty similar to sigmoid, except there's no smoothness. It's like a rough straight line. And if beta was less than 0, then the slope would go this way, and it would look kind of awkward, and it wouldn't really work very well. I mean, maybe it would in some very weird cases, but for now, I will just be constraining beta to be strictly positive. All right, so some of the math here, it won't be too complicated. I'll kind of get through this so I can show the example at the end. But so we have our random variable y, which we're assuming is a Bernoulli random variable with some parameter theta. And then note that the expected value of a Bernoulli random variable is the parameter itself, theta. And since that's what we want to estimate, we can conveniently replace theta with g of x, our link function. And I forgot to put it here, but recall that the definition of a Bernoulli PMF is theta to the y times 1 minus theta to the 1 minus y. And here I just replace theta with our link function g. So y is distributed as g of x to the y, 1 minus g of x to the 1 minus y. And there are numerous ways to kind of approach this problem, but I'll just use a fairly common approach, which is maximum likelihood. So we define the likelihood as the product of a bunch of Bernoulli random variables, and n of them that are each independent from each other. And so that's essentially this. We're just taking the product of this thing n times. And then we want to maximize this with respect to beta. And in some cases, depending on what you're doing, it's usually easier to maximize the logarithm, which is a pretty common trick because logarithms preserve extrema. And I don't think this was strictly necessary for how I'm actually optimizing this, since I'm just essentially using SciPy, but I just did it anyways here. So this is just taking the logarithm of our likelihood, and then we want to essentially maximize this function. And then I won't go into detail, but you could use the properties of logarithms to understand how you get this. And so that's the basic idea. So now I want to go over to a sample notebook I have. So here's the notebook with some of the sample code I put together, basically covering what we did in the last slide. So I have SciPy for the optimization, and then I'm also using sklearn logistic regression just as a comparison. And so here's my Bernoulli random variable of interest, and then some input data. And then I'm also scaling this input data because I was having some issues finding the actual optimal value, just leaving it as is. So scaling it did help. And then here is the link function. So this value here, x times beta, this is just the raw linear combination. And then here I am binding it between 0 and 1. So if it's greater than or equal to 1, then I'm setting it some value close to 1. And then if it's less than or equal to 0, I set it some value close to 0, but not actually 0. The reason why I did this is because of logarithms. So if I take the logarithm of 0, then that is undefined. I probably didn't need to do the same thing here. I could have probably just used 1, but whatever. I'm just keeping it close to 1 and 0, but not exactly 1 and 0, just to prevent weird things happening. And then here's the objective function, which is essentially what we saw in the last slide. So this is going over all of the x norm values, which is the basically scaled version of this, and the y values, and it's taking y times the logarithm of the link function plus 1 minus y times the logarithm of 1 minus the link function, which is, as we saw in the last slide. And the only difference is that in the last slide, we would be adding all of them together. However, since we only have the minimize optimizer, then in order to maximize it, you have to negate it. And so I'm subtracting everything because minimizing the negated version of the objective function is equivalent to maximizing it. So hopefully that's not too confusing. It makes sense. And then here's the actual optimization. So we pass the objective function. This is the initial beta value. So I just set it to beta is 0.5 just as a initial condition. And then this is the constraint that specifies that beta should be greater than 0. And then once we run this optimization, after 6 iterations, this is the first it did converge successfully, and then we get our beta value, which is right here. So after running this optimization, beta is 2.807, and then I just have this dummy predict function, which will just go over all of the data values that we have. It'll just basically call the link function. And so just to see what that looks like, if we pass in all of those normalized x values, this is basically all of the expected values, conditional expectation estimates. And then, if we choose the threshold of 0.5, because the actual expected value is roughly half and half. So if we just use 0.5 as a threshold, which is also sklearn's default, and I made it easy by splitting it half and half. This is the output, and then doing the same thing for using sklearn. So I'm fitting with the x norm values and our y values, and then basically predicting. And then you can see that, let me make this in a slightly better format. Oh, whoops. Okay, never mind, whatever. I was trying to make this not an array. Well, whatever, it doesn't matter. Anyways, you can see that the two outputs are exactly equivalent. And that's not to say that this naive linear link function works great. This is not like perfectly separable, but it's like a very good case just for demonstration. If you were to use this link function on like real world data, it would not capture some of the patterns as well. But this to just demonstrate how link functions work and how you can kind of use them to create different types of models to model different types of data. And some link functions might work better than others. And so depending on the specific use case, you can probably think of link functions that might work better for a particular type of problem. But that's all I have. Hopefully you learned at least something about link functions and how they work and why they're useful or why they're used. And that's all.